Assalamualaikum and good morning, everyone. Welcome to my third recorded lecture for CHM577. And this morning, I'm going to talk about electronegativity, bond polarity, and dipole moment. And please refer to the textbook Silberberg on chapters 8 and 9 to assist you in understanding these topics that I am presenting this morning. So for today's lesson, we are going to talk about three big topics, which are trends of electronegativity, and then followed by how to determine bond polarity and how to identify dipole moment. I'm sure this is not the first time you're hearing about electronegativity, but it doesn't hurt to have some refresher session. So, as a definition, electronegativity or EN is the ability of an atom to attract the bonding electrons towards itself in a chemical bond. So, when we're talking about electronegativity, it's really about two atoms that are bonded together, and which one of these two atoms has the strongest ability to pull electrons, bonding electrons towards itself. So that is electronegativity, and it is different from electron affinity. Electron affinity is the topic that I covered in my lecture 2, where electron affinity, let's do a little bit of a recap about electron affinity. So electron affinity, to make it clear the difference between electron affinity and electronegativity, the definition of electron affinity is the energy given off, that means energy is released when a neutral atom in the gas phase gains an extra electron to form a negatively charged ion. So we're talking about an element, an element by itself, not bonded to anything else, an element in the gas phase releasing, no, not releasing, obtaining an electron. So when an electron is obtained by an atom in the gas phase, the energy that is given off upon the arrival of that electron is the electron affinity. Now, you must remember that to make electrons leave an atom, you have to provide energy. But when that electron is received by an atom, the opposite reaction occurs. That means if releasing electrons releases energy, receiving electrons will make that atom gain energy. So that is the definition of electron affinity. And if you recall from my previous lecture, this is what is the trend of electron affinity versus atomic number looks like. So you can see that all the elements in the seventh group number 7, has the highest electron affinity, but among them, chlorine has the highest value. So go back to today's lesson. So electron affinity is measurable. You can measure it because you measure how much energy is gained when electrons come into that element. So you can measure it. And chlorine has the highest electron affinity in the periodic table. It is the energy change when 1 mole of electron is gained by 1 mole of gaseous atom. However, when we talk about electronegativity, if you recall just now, I say electronegativity is when you have two atoms bonded together and which one of the atom has the ability to attract the bonding electron to itself. It is a relative. And among the many, many elements that we have in the periodic table, fluorine has the highest electronegativity, even though it has the lower electron affinity compared to chlorine, but fluorine, when it is bonded to an atom, it is the highest element or highest atom that can pull that bonding electrons between from the other atom. Yeah. So if you can see this picture here, can you see that picture here? Yeah, that picture. That is a fluorine, the atom fluorine, and that is for the, I think, hydrogen atom. And you can see that the electrons are much, much more concentrated on the fluorine side. So saying that electrons are pulled or attracted towards the fluorine compared to hydrogen. Okay. So electronegativity is a function of two properties of isolated atom. It is a combination of the atom's ionization energy, i.e. how strongly an atom holds its own electron, and another one is the atom's electron affinity, how strongly the atom attracts other electrons. So when we talk about atoms, when we talk about bonding and chemical bonds, we talk about movements of electrons or where electrons go. So when an atom has a strong ability to hold its own electron, we say it has a high ionization energy. And when an atom has the ability to attract other electrons to itself, we say it has the high electron affinity. So electronegativity is a combination of ionization energy and electron affinity. So for example, an element that has these two characteristics, a large electron affinity, i.e. an ability to pull electrons into itself, and high ionization energy, or the ability to hold on to its own electron. For this element that has a large electron affinity and high ionization energy, what will happen to them? It will attract electrons. Obviously, it will attract electrons from other atoms and resist having its own electron taken away. So that electron or that atom that has this property, a large electron affinity, a high ionization energy, will have a high electronegativity. Ya, it has a high electronegativity. Ya, memanglah kalau contohnya when we talk about human when we equate human and money with atom and electron, anyone who can hold his own money and be able to get other people to give money to themselves will be very, very rich with money. Similarly, for electronegative atoms. Now, there is a scientist called Pauling. Yeah, Pauling has studied the trend of electronegativity across the periodic table, and he had given a value to electronegativity comparatively between one element to another. The higher the Pauling's value, the more electronegative the element is. So atoms with high electronegativity values are the best electron attractors, and atoms with low electronegativity values are the worst electron attractors. So as I was telling you earlier, fluorine is the most electronegative element. It has electronegativity value of 4.0, and that is the highest Pauling's value of all elements. So fluorine is the most electronegative element that is in the periodic table or in the world. Yep. So if you look at, move my face a bit. If you look at Pauling's electronegativity value, maybe let me make it smaller a little. Yeah. So electronegativity decreases down a group. So as you move from top to bottom, it becomes smaller, and it increases from left to right. So when you move from potassium towards bromine, or from sodium towards chlorine, or from lithium towards fluorine, it becomes bigger to the right. It's small on the left. Pauling's Pauling's value is small on the left-hand side of the periodic table and big on the right-hand side of the periodic table, small at the bottom, big at the top. So obviously fluorine being there, well, we exclude noble gases in this case because noble gases really do not care. They do not care to be involved in any kind of bonding. So fluorine in this case will be the highest or the most highly electronegative element in this periodic table. So when you look at Pauling's value, hydrogen 2.1, and it goes down as you go down from hydrogen to lanthanum to francium at the bottom. But sodium, for example, it has 0.9 Pauling's value, but that value becomes higher as you move to the right. Magnesium 1.2, aluminium 1.5, silicon, phosphorus, sulfur, and chlorine 3.0. So that's how it goes. So each one element has its own Pauling's value. And what do we do with this Pauling's value? We use Pauling's value to determine what kind of bond will be formed when one atom is bonded to another. Yeah, the difference between the Pauling's value will be very, very useful in us determining the type of bond. Now, the type of chemical bonds, you all know there are two major types of bonds that we study here in chemistry. We have ionic bond. Yeah, ionic bond. Ionic bond is when there is a complete transfer of electrons from metal to non-metal. For example, sodium gives up one electron to be taken up by chlorine to make sodium chloride. So that one electron from sodium is completely transferred from your sodium to the chlorine. So we say with that complete transfer of electrons between sodium to chlorine, then we say that bond between sodium and chlorine is an ionic bond. Ionic bond. Yeah. This is usually happening between metal with non-metal. And the second type of bond that you have learned before is covalent bond. In covalent bond, there is no complete transfer of electrons. It's all about sharing of electrons. But sharing also, it has a degree of sharing. Some sharing are equal. Some sharings are not equal. You know, when you have two identical atoms forming a covalent bond, for example, when one hydrogen atom is bonded to another one hydrogen atom, then this become, because they are equal atoms, they have equal strength in attracting electrons to themselves. So there is an equal sharing of the bonded electrons between the two hydrogen atoms. So we say each atom has an equal share of the bond's electron pair, because when the two atoms bond, they share a pair of electrons. Two electrons, one from hydrogen on the left, another one from hydrogen on the right, will be shared between the two hydrogen, and they are shared equally. But the second type of covalent bond is when you have different atoms. When you have different kind of atoms combined, for example, hydrogen and fluorine, when you have hydrogen and fluorine combining, the two are obviously two different atoms and very different Pauling's electronegativity values, yes? When different kind of atoms combine, one of the nuclei usually will attract the electrons, the bonding electrons. Let me put the bonding here. The bonding electron more strongly, yeah? In the case of hydrogen and fluorine, fluorine will attract the bonding electrons strongly to itself, making hydrogen deficient in shared electron. Yeah, yeah. This is an illustration. When you have two hydrogens, you can see very well here that the electrons are shared equally between the two atoms of hydrogen when it makes hydrogen gas H2. Whereas when you have HCl, here in the example is hydrogen and chlorine, you will see that the electron density of this bonding electron, this is a bonding electron here, is pulled more tightly around the chlorine end of the molecule, giving a partial separation of charge and a polar covalent bond. So that bond becomes polar. There is a delta negative on the chlorine side, and there is a delta positive on the hydrogen side. So we say that the bond between hydrogen and chlorine is a polar bond, whereas the bond between hydrogen and hydrogen is a non-polar bond, because that bonded electrons is they are being shared equally between the two hydrogens. So this is a polar covalent bond. This is a non-polar covalent bond. The hydrogen case is a non-polar covalent bond, whereas the HCl case is a polar covalent bond, because of the difference in electronegativity values. So, covalent bonding with equal sharing of electron occurs in diatomic molecules formed from one element. For example, your hydrogen just now, H2, Cl2, I2, N2. And because this is, you can see all these are represented in dots. But when you write in chemistry, these shared electrons, the two dots can be represented by a bond. A dash may be replaced by may replace a pair of dots. So in here you have three pairs of electrons being shared between nitrogen. So you have three bonds between the two nitrogen atoms. This is when you have non-polar covalent bond, where the bonding electrons are shared equally between the two same type atoms. If the two atoms that constitute a covalent bond are identical, then there is equal sharing of electrons. It's called nonpolar. Ionic bonding and nonpolar covalent bonding represents the two extremes. When you have the ionic bonding, the electron is completely transferred. When you have nonpolar covalent bonding, you have the bonding electrons are shared equally. None is stronger than the other. So these are the two extremes. But in between the two, you have unequal sharing of electrons. So if the two atoms that constitute a covalent bond are non-identical or not identical, there is an unequal sharing of electron. So this is called polar covalent bond. Let me make that red. Polar covalent bonding. One atom assumes a partial positive charge and the other atom assumes a partial negative charge. That's when you have that delta that I was talking about. This is the partial positive charge for the hydrogen, and this is the partial negative charge for the chlorine. So here we are. So this charge difference is a result of unequal attraction of atoms attraction the atoms have for their shared electron pair, like I was saying earlier. So this is the case of HCl, as I explained. So as you can see here, the bonded pair of electrons, these ones here, they are attracted to chlorine much more than they are attracted to hydrogen. That is why we say that more electronegative chlorine is having a bigger share of the bonded or the pair electrons being shared between them. So it is a delta negative polar negative, and then this is a delta positive slightly positive. So partial positive charge on hydrogen, partial negative charge on chlorine, and chlorine has a greater attraction for the shared electron pair than hydrogen, and the shared electron pair is closer to chlorine than hydrogen. So the attractive force that an atom of an element has for the shared electron in a molecule of a polyatomic ion or polyatomic molecule is known as electronegativity, and it causes this partial negative and partial positive, and the bond is said to be polar bond. I'm sure that concept is not alien to you. So the polarity of a bond is determined by difference in electronegativity values of the atom sharing the bond. So when you look at Pauling's value, like I was telling you, when you look at the Pauling's value, you look at the difference between the two and you can determine what type of bond will be formed. So the chemist Linus Pauling, his first name is Linus, Pauling is his surname. He devised a method for calculating electronegativities of elements, and these are those values. As you can see, this is a simplified version of the periodic table. Lithium has Pauling value of 1, fluorine has Pauling value of 4, and these two, sodium 0.9, chlorine is 3. However, we do not put Pauling's value into your transition metals. Yeah, non-metals are the most electronegative elements, and metals are the least electronegative. That means metals are electropositive. Okay. So the difference between electronegativity values of two bonded atoms give an estimation of the polarity to be expected of a bond. So when you have very small difference in electronegativity value, you're going to have a slightly, very slightly, or even non-polar bond. Yeah. Electronegativity values are useful in determining if a bond is classified as either nonpolar, polar, or ionic. Nonpolar covalent, polar covalent, or ionic. Only covalent bonds can be polar or non-polar. Ionic bonds, there is no polarity. There is a complete transfer of electrons. So what do you do is when you look at these values, you have to calculate the difference between their electronegativity values. Only the absolute difference is important. So how do we do that? Very easy. Okay. To calculate the difference is really very easy. For pure non-polar covalent compound, when there is equal sharing, for example, hydrogen with hydrogen, the maximum difference is very small, 0.2 to 0.5. In fact, maybe 0 even. Yeah. If you have a difference of smaller than 0.5, then you have a non-polar covalent bond. But when you have a difference between 0.5 to 1.6, yeah, the difference of your Pauling's value between 0.5 to 1.6, then you have a polar covalent because there is unequal sharing between the two atoms of the electrons in the bond, for example, ammonia or water or HCl. Let's have a look at the difference between hydrogen and chlorine. Here, your hydrogen is 2.1 and your chlorine is 3. So 3 minus 2.1 is 0.9. So 0.9 falls between this value, between 0.5 to 1.6. So between hydrogen and chlorine, with the difference of Pauling's value to be 0.9, you know you have a polar covalent. Yeah, you know you have a polar covalent. But when you have a difference of greater than 2, then there is a complete transfer between the two atoms. Contohnya, for example, sodium and chloride, magnesium and chloride. Let's have a look at the difference between sodium. Sodium is 0.9, Chlorine is 3. 3 minus 0.9, you have 2.1. There is a huge difference between the Pauling's value, and you know it is ionic bond because that huge difference in ionic bond is showing a complete transfer. That means chlorine is far too strong for sodium to resist giving its electron. So it's just ambil P lah kat hang. Jadilah dia ionic bond. Yeah. So anything less than 0.5 is a nonpolar bond. Anything bigger than 0.5 to 1.6 is a polar covalent bond. Anything bigger than 2 is ionic. So what is going to happen between 1.6 and 2? There is an area between 1.6 and 2. So let's have a look. Yeah. If the difference in, this is delta. Let me see, that is delta in symbol. Yeah. If delta of electronegativity or is between 1.6 and 2, and if a metal is involved, then it is considered ionic. But if non-metals, both elements bonded to each other are non-metals, then they're said to be polar covalent. So the shaded gray area between 1.6 to 2, if you have one of them is metal, another one is a non-metal, then you know it is ionic bond. If you have both of them are non-metals, then they are highly, highly polar bond. So let's have a look at what that could be. I don't know. What could it be? Could it be between I don't know. We can give you some example, not now, later. Yeah? Right. Yep. Less than 0.5, you have a pure covalent or non-polar covalent. Between 0.5 to 1.6 is a polar covalent. Anything bigger than 2 is ionic. Yeah. But if you have in between 1.6 to 2, if there is a metal, it is ionic. If there is a non-metal if there are non-metals, then they are polar covalent. So this is the symbol for polarity. Your H, which is a slightly positive, and your F, which is a slightly negative, gives a polarity, bond polarity, and it is represented by this symbol. An arrow going from hydrogen to fluorine with a bar closer to hydrogen. That means there is a wall, if you like, that the electrons cannot go into the hydrogen because all of them go to the fluorine. Yep. The polarity of bond gives partial ionic character. So when you have a polar covalent bond, you say that that covalent bond has partially ionic character. Not full, because full ionic is a complete transfer. It's in between equal sharing and complete transfer. So we say a covalent bond with partial ionic character. So classification of bonds by difference in electronegativity. So let's have a look. Maybe when you have lithium bromide or lithium chloride, those will be ionic, but HF will be definitely covalent. So this is the arbitrary cutoff of whether you have ionic bond or pure covalent or anything in between. So you can try to do this exercise to determine the bond polarity from the difference in electronegativity values between nitrogen to hydrogen, between fluorine to nitrogen, between iodine to chloride. What kind of bond will you get? And you can please rank the order of increasing polarity between the three bonds here. It's really very simple exercise. All you have to do is refer to this value up here, and then you find out the difference between them, and determine what kind of bond you will get. So now, when we have understood about polarity, then I'm going to go into the next topic, which is dipole moment. Now, the magnitude of polarity is expressed in terms of dipole moment. The higher the polarity, then the bigger is the dipole moment between the two. So a dipole or a kutub, when you talk about it in Malay, we say kutub. A dipole is a molecule that is electrically asymmetrical, causing it to be oppositely charged at 2 points. So a dipole can be written as a positive n on the left, for example, and negative n on the right, for example. And this is what we say a dipole moment. You can also use an arrow to represent a dipole moment, like I was explaining to you earlier. It points to the negative charge center with the tail of the arrow indicating a positive charge, center of the charge, like this one. So either you can draw it in this way, yeah, draw it in that way, or you can also draw it in this way. So dipole moment has a magnitude and it has a direction. Where does it go to and how much? Yeah, so that is a dipole moment. And we always talk about dipole moment when we talk about a polar bond or a polar molecule. Now, the magnitude of polarity is expressed in terms of dipole moment. So you have the dipole moment is equal to the amount of charge, which is Q times the distance between the charges, D. So mu here, no, this is not mu, this is micro. Is equal to Q times D, where Q is the amount of the charge. You look at what are the charges and the distance between them. So 1 debye is 3.336 times 10 to the power of minus 30 coulomb meter. So if you calculate the charge of this molecule multiplied by the distance between the two atoms making that molecule, then you get the bi value or the polarity value. Yeah. Let's have a look at the next one. So a molecule containing different kind of atoms. I've repeated this many times. The bond may be polar, but if you have a molecule that is symmetrical, it contains the same polarity on the left and on the right. Even though the bonds are polar, the molecule doesn't have to necessarily be polar. For example, if you have carbon dioxide, yeah, there is a carbon and there is an oxygen. The electronegativity value of carbon is 2.5, oxygen is 3.5. So the difference between Pauling's value of C and O is 1. So definitely the bond between this carbon and that oxygen is a polar bond. And the bond between this carbon and the oxygen on the left is also a polar bond. So you have two polar bonds. One is acting to the right and another one is acting to the left. However, the dipole moment, yeah, is the difference between the polarity of the bond on the left and the polarity of the bond on the right. So dipole moment is 1 minus 1, so that is 0. So when the dipole moment is 0, that means that molecule, that CO2 molecule, is not polar. So a polar bond that exists within a molecule may not necessarily make that molecule a polar molecule. Because if you have a good symmetry, a strong symmetry between the two polar bonds, the effect of the pull of electrons to the right will be cancelled by the pull to the left. So the effect on the whole molecule is 0. So that molecule is non-polar. Yeah? So depending on the shape of the molecule. Let's have a look at another example. Now this, for example, these are two more examples that we have. of a boron with 3 fluorine. So you have this bond 2 that is polar, from boron to F polar, another polar. But the 3 polar bonds are acting equally at opposite sides, one, because it's highly symmetrical. The effect of the pull from this boron, from this fluorine, is cancelled by that, is cancelled by that. So this is a non-polar molecule. Similarly, this is also a non-polar molecule. The net dipole moment or the vector sum is 0, so you have a non-polar molecule. But if you have, for example, SO2, let me try and see, SO3 and SO2, you have SO3 to be nonpolar because it's highly symmetrical, and the pull of the electron from oxygen of oxygen from that sulfur is cancelled equally from the to the north and to the left and right, like that. So you have the whole story to have a net dipole moment of 0. But if you have a case like this, there is a polar bond between S and O on the left and S and O on the right at an angle like that. And there is also, but there is no bond at the top here. So all you see, if you ignore the one at the top, just 1 second, let me see if I can do this. If you ignore that one at the top, all that you can see is a pull onto the left, electrons pulling onto the left and electrons pulling onto the right, but the pull is not cancelled by another one at the top. So with that, you do not get a net dipole moment of 0. You get some value of dipole moment. So this molecule, SO2, is a polar molecule compared to SO3. So it is the shape of the atom that will determine whether you get a dipole moment in that molecule or not. Yeah, I hope you understand that. So can you determine, for this you have a very, very symmetrical SF6 sulfur with 6 fluorine. Because of its high symmetry, the action of electrons pulling from all directions is cancelled. For example, this pull is cancelled by this one to the top, is cancelled by this one to the bottom. This one to the back right is cancelled by this one to the front left. This one from the front right is cancelled by the one from the back left. So there is a perfect cancellation of each one of the electron movement, making your SF6 a non-polar molecule despite having 6 polar bonds. Yeah. Similarly with this one, you can see high symmetry. That means it's a very non-polar molecule. This one also, high symmetry, non-polar molecule. But when you have something, okay, we're still talking about non-polar molecules when you have very, very high symmetry where the cancelling out of dipole moments occur. So you have all these non-polar situations or non-polar molecules occurring, right? But when you have a non-symmetrical, okay, let's go back to this one. A linear molecule, a trigonal planar molecule, a tetrahedral molecule, a trigonal bipyramidal molecule, and octahedral molecule. They are all polar molecules if you have all the atoms involved to be the same. But when you have V-shape or trigonal pyramidal or tetrahedral with different atoms, yeah, let me make it a little bigger. Yeah, this is your V-shape molecule, when you have the pull onto the left, it's not exactly cancelled out perfectly by the pull onto the left. You still have a net effect. Yeah, the dipole moment of individual polar bond looks like this. This is the dipole moment. You still have a net resultant dipole moment, making water to be a polar molecule. Similarly, with your ammonia, you have the nitrogen bonded to three hydrogens, but there is a lone pair of electrons at the top. Similar with this one, there are two lone pairs of electrons at the top here for water. Yeah, for water you have two lone pairs of electrons at the top. I hope you have when I talk about this, you can recall from your previous lessons. Yeah. So this is what the dipole moment of individual polar bond looks like for ammonia, and you have a net resulting dipole moment like that. Yeah, so ammonia is a polar molecule. Now, this one, tetrahedral. What is the difference between this tetrahedral molecule? Let me make it bigger. What is the difference between CHCl3 with this one? CCl4. CCl4 has all chlorine on the four corner of your tetrahedral. So the dipole moments of each bond is equally strong. But when we come to here, the dipole moment of CCl, the down bottom here, they are strong, but there is a weaker dipole moment between C and H. So you have a no cancellation, no perfect cancellation, excuse me, no perfect cancellation of dipole moment like that. Look, here it is strong going that way, but it's weak going the other way, so you still have a resultant net dipole moment for chloroform. Yeah, oh no, trichloromethane, I'm sorry, yeah. CHCl3 is chloroform, yeah. So you have these three examples are polar molecules because of the shape, because of the type of atoms bonded to the central carbon or central atom. So I hope you understand the significance of net resultant dipole moment and how you get um, the dipole moments of individual polar bonds giving effect to the presence of polarity in that molecule. Right. The CCl bond is polar, but CCl4 molecule is non-polar. Explain. It's very easy, isn't it? Because I've explained it to you. You have your carbon has a Pauling's electronegativity value, negativity value of 2.5, and your chlorine has a Pauling value of 3. So you know that this has a difference of 0.5. It's a polar bond. The CCl bond is polar because the chlorine atom are more electronegative, pulling the shared electron pair towards itself. But in CCl4, there are 4 CCl bonds. Since these polar bonds are symmetrically arranged, yeah, this is important. They are symmetrically arranged. The polarities of individual bonds cancel each other, resulting in zero dipole moment for the molecule. So the net result is that your CCl4 molecule is non-polar, cancel, because it's totally cancelled. Tapi, looking at this, you can see that some of these are polar, some of these are non-polar. Water, for example, has a polarity going to the top. Yeah, your SO2 has a polarity going to the bottom, and CO2 has no polarity because they cancel each other out perfectly. Same as your methane, it has No dipole moment is a nonpolar molecule because of the same principle, right? Right. I think that is the end of this lecture. This is a 45 minutes lecture. I hope you understand everything. I hope you're going to be able to do the exercises that I'm going to give to you in a while. So take care and see you in the next lecture. Bye-bye. Assalamualaikum.